Hello, we are from Group 7. Would like to share our problem-based learning outcome entitled PHYTOREMEDIATION for wastewater containing heavy metal, zinc and copper using water hyacinth and water lettuce. Before that, let's get to know the members of Group 7. It consists of Hamizan, Afiq Ruzaini, Muhammad Faradzal, Muhammad Aslam, and Nick Ahmad Rafiki. Treating wastewater with heavy metals is challenging due to their persistent and toxic nature, impacting the environment and human health. Conventional methods may struggle to meet demand. For lower metal concentrations, various approaches, such as chemical precipitation and membrane filtration, exist, but their effectiveness varies. Heavy metals, even at trace levels, pose health risks and contaminate aquatic ecosystems. PHYTOREMEDIATION, a method utilizing plants to rehabilitate polluted environments, offers an eco-friendly solution, yet challenges persist. This study explores the efficiency of two floating water plants in removing heavy metals from wastewater in a problem-based learning scenario. To examine and compare the efficiency of water hyacinth Eichhornia crassipes and water lettuce Pistia stratiotes in reducing the concentration of heavy metals zinc and copper in wastewater. Let's go to experiment. Calculated masses of zinc sulfate heptahydrate and copper sulfate pentahydrate were utilized to form synthetic zinc and copper solutions in distilled water. For zinc, 0.013 grams of zinc sulfate heptahydrate powder was dissolved in 1 liter of water, creating a concentrated zinc solution. Simultaneously, 7 liter of water was prepared in a plastic container, and 1 liter of the ZN solution was added, resulting in an 8-liter solution with 3 milligrams L zinc. The same procedure was repeated for copper using 0.12 grams of copper sulfate pentahydrate powder. Initial concentration measurements were taken for both ZN and Cu solutions, despite the target concentration being 3 milligrams L. The test results reveal a concentration of 2.68 milligrams L for zinc and 2.93 milligrams L for copper. Water hyacinth and water lettuce were acquired from a local supplier. All plants underwent a comprehensive rinsing process to eliminate debris or dirt adhering to their roots. The plants were prepared 1 day in advance and positioned in the laboratory to acclimate to the environment. 2-liter plastic containers were labeled for each metal solution. Subsequently, 2-liter of zinc solution and copper solution were added to their respective containers. In each container, 2 water hyacinth plants and 2 water lettuce plants were introduced. The concentrations of copper and zinc were documented on day for the respective containers. For reading of concentration of zinc, the procedure involved selecting the stored program. For zinc method, 780 zinc on a HDR3900 spectrophotometer. Subsequently, a 25 milliliters graduated mixing cylinder was utilized to measure 20 milliliters of the sample. The contents of a zinc over 5 reagent powder pillow were then added to the cylinder, and the mixture was inverted several times until the powder completely dissolved. For blank preparation, 10 milliliters of the solution was transferred into a square sample cell. In the prepared sample, 0.5 milliliters of cyclohexanone was added to the remaining solution. In the graduated cylinder using a plastic dropper, timer was pressed to initiate a 30-second reaction period. During this time, the cylinder was stopper, and the prepared sample was vigorously shaken. When the timer expired, the blank was wiped and inserted into the cell holder with the fill line facing right. Zero was pressed, and the display showed 0.00 milligrams LZN. The prepared sample was wiped, inserted into the cell holder with the fill line facing right, and read was pressed to obtain the resultant Mg L zinc. As for copper, the process commenced with selecting the stored program. For copper method, 135 copper bison on the HDR3900 spectrophotometer. Subsequently, 20 milliliters of the sample was measured. For the prepared sample, a square sample cell was filled with 10 milliliters of the sample. The contents of 1 cuve or 1 copper reagent powder pillow were added to the prepared sample cell. and the sample was swirled to ensure thorough mixing. Timer was pressed to initiate a 2-minute reaction period. For blank preparation, once the timer expired, a second square sample cell was filled with another 10 milliliters of the sample. The blank was inserted into the cell holder. With the fill line facing right, 0 was pressed, and the display showed 0.00 milligrams L copper. Within 30 minutes before the timer expired, the prepared sample was inserted into the cell holder with the fill line facing right, read was pressed, and the results were displayed in Mg, L copper. The detailed results in Figure 1 provide a thorough examination of the complex dynamics of phytoremediation efficiency, specifically focusing on the targeted reduction of zinc concentration over 8 days. Both water hyacinth and water lettuce started with an equal ZN concentration of 2.68 milligrams L on day 0. As the phytoremediation process unfolded, both plants exhibited a significant reduction in ZN concentration at the 4-day and 8-day marks. Water hyacinth, in particular, showed an impressive decrease from 2.68 milligrams L on day 0 to only 0.53 milligrams L by day 8. This suggests that water hyacinth has the potential to be an effective agent for phytoremediation in removing zinc from water. Regarding copper, both water hyacinth and water lettuce started with an equivalent copper concentration of 2.93 milligrams L on day 0. As the phytoremediation process unfolded, distinct patterns of copper reduction became evident for each plant species. Water hyacinth demonstrated its proficiency with a significant decrease in copper concentration, dropping from 2.93 milligrams L on day 0 to 0.17 milligrams L by day 8. This remarkable reduction emphasizes water hyacinth's effectiveness in extracting and accumulating copper, positioning it as a robust phytoremediation agent for copper pollution. Similarly, water lettuce showed a commendable reduction in copper concentration, decreasing from 2.93 milligrams L on day 0 to 0.19 milligrams L by day 8. This consistent downward trend highlights water lettuce's efficiency in contributing to copper phytoremediation. The removal percentages for zinc and copper indicate the efficiency of water hyacinth and water lettuce in extracting these metals from the water. For zinc, water hyacinth demonstrates an 80% removal efficiency, while water lettuce exhibits a slightly lower efficiency of 66%. In contrast, both plants show a high removal efficiency of 94% for copper, highlighting their effectiveness in mitigating copper pollution in water. In conclusion, the investigation into phytoremediation's efficiency, focusing on zinc and copper reduction over 8 days, provides valuable insights. Water hyacinth demonstrated 80% ZN removal and 94% K removal, while water lettuce showed 66% ZN and 94% K removal. Both plants exhibit promise for eco-friendly water treatment, emphasizing their applicability in environmental conservation. Despite slight performance differences, ongoing research will refine practical applications, considering diverse contexts and addressing plant conditions, enhancing the utilization of water hyacinth and water lettuce in phytoremediation strategies. Now that we really done it's a warp, guys.